So in the last two lectures, we talk about images and depth images. And we almost wrap up the last lecture with talking about an example of depth images and how, simple example, how could be used. The fact that depth images is a point in the 3D dimension, it enables us to utilize transformation in a 3D. And luckily, in most of the computer hardware, there is a buffer which is usually called the depth buffer, which is rendered also as a depth image in the computer and could be utilized to do various applications. If you want to experiment with depth images, that's there for you to maybe to play and utilize. For example, if we see the rendering of the image in the left side, we'll create the depth image in the depth buffer in the right side. Now, one issue, instead of trying to render this object twice for stereo, one could render actually one time and then use the depth image to warp it and create two images for the one for the left eye and one for the right eye in order to create a stereo images. And also in the last time we say that it's, as we said earlier, that practically depth image is a 3D or points in 3D, so we can utilize the translate and scale transformation, which is to apply to these images in order to make changes or transform them to a different images. The same with rotation. We can use practically rotating around the X, Y, and Z axis, everyone respect separately. But we can also use quaternion, which most of you are aware of, in order to return around any axis you want. It's a very simple technique that you take the vector of rotation, the angle you want to rotate by around this axis, and create a quaternion. This quaternion you apply directly as a quaternion transformation, or you can convert this quaternion into rotation matrix and utilize it. Is that clear? Okay. So what we get practically a depth image, and we could use this depth image to interpolate in order to create extra points or extra values we need or items in this depth image. So for example, one of the common things that the scanning or the depth images are not or the points in the depth images are not uniformly distributed. Can one tell me why? One of the main reasons why it's why the points in depth images are not distributed evenly, as pixels in the image are distributed uniformly and evenly in a nice manner. More in the images, even more regularly.
Because of more distant objects, the points will be sparser?
Yeah, so this is exactly the main reason. First of all, because a projection or the perspective projection, this is one reason. Even it's planar, object will be kind of different distances. Some object will be close and will be scanned at higher resolution, will have more points per unit, a size unit, and further object will have less points per a square unit. So this is the main reason we'll have the points are not distributed evenly or equally on the surface of the surface represented by the depth image. One of the ideas people would like to add is to add points where they have sparse points. In order to add point exactly the same way we added pixels or value of a pixel. So if I want to add a point, I need to determine in images, when we saw interpolation, we were very much interested in knowing the value of this pixel. We add a point, and now we want to get the value. If I just kind of refresh your memories in our image transformation, we say, okay, we have an image, and you see, we say we will do back a projection, and this is the pixel, and we want to say where this pixel came from in the original image. So Usually this pixel does not come from like a center of a pixel from some point, and now we are interested to know what's the value of this pixel. We used interpolation in order to determine the value, but here we don't need, we want more. We want not the value of a pixel, we want the location of a point. And instead of interpolating one scalar value, we're practically interpolating a vector, which is exactly the same technique. So we're interpolating a vector, which is a point which will be x, y, z, which the location of the added point. Now, we could use very similar manner. We could use either like taking the value of the nearest point, which will give us the least accuracy, or like if we have several, like 3 points, we can interpolate between them and say the point we are looking for will sit on the plan, which is determined by the 3 points or more points. We can use the same, we can use a cubic or quadric interpolation to determine the position of the point. It's like one of the common ways to use in order to determine that is use a Gaussian. It's become because many techniques using Gaussian, and it's quite good approximation. It came also from the frequency theory that Gaussians, like approximation, provide the better results. Often people use a expectation maximization, which is mean we try to see the best Gaussian that fit the set of points and determine the location of the new points based on this Gaussian. That means we maximize the expectation of the point being on that Gaussian. Is that clear? Okay, that's which is like, I would say, for now, when we're talking about kind of the first part, when we talk about depth images. Now, yes?
It seems like interpolation bad thing, because, I mean, depth is not continuous for objects, so it's like saying like these points here are just like in the middle.
Yes, this is...
Like, for example, pixels here have a depth, but pixels just right next to me will have a discontinuous. Like this function of depth is like kind of discontinuous. So if you do the interpolation, it will be like error.
You are absolutely right. We don't, not always, we would like to add points and interpolate and kind of compute them as interpolation of their neighborhood. Exactly because in depth images we have discontinuity. So if you scan one object, for example, if we are scanning this table from the top, we will have one point from here and other point from the floor. One of the important things, if we want to create points in the middle, definitely will be incorrect. But the main idea, if we want to add points in the floor, or like what we like believe they belong to the same object. So usually, kind of what we will do, we not blindly interpolate, add points and interpolate them like by, or like compute their location based on their neighborhood. What we do often, we segment the depth image into regions or patches, and then you can interpolate within patch in order to increase the resolution. But if you interpolate, you create a point, definitely if you are not careful, this point may not actually exist in real, and you're creating kind of a more outlier. Outlier is a point which doesn't belong to the neighborhood. So this is, it should be careful that exactly not always any interpolation are like points are like is welcomed. You usually want to be careful about how to do the interpolation and where to add these points. Okay. So this is what with this part. Now I will go into in the next thing, which is I want to go in, is we have two images or multiple images, how we create this depth images. In the last lecture, we talked about depth images could be created from three sources. One of the sources, one of the sources was images, stereo images or multiple images. And we will try to see how we can create depth images from multiple images. This, the knowledge or what we will learn in these lectures is not only used to reconstruct depth images from stereo images, but we will visit various techniques that are useful in many other, like a discipline or another kind of areas of image processing and computer vision. So before going that, I'll try to kind of like go very quickly other kind of based algebra and vector issues, which is, I assume, all of you know, but just kind of to create common knowledge. So we usually refer to a point in one dimension as like x. 2 dimension will have x and y, and 3 dimension will have an x, y, and z. If we have line, usually we kind of in 2 dimension line is connecting 2 points, x0, x1, and in the same thing when in 2 dimension space we'll have x0, y0, and x1, y1, and in the 3D we'll have x0, y0, z0, and x1, y1, z1. So we have practically, this is kind of like a representation of a point and a line in 2D, in 1D, 2D, and 3D. The same thing with the plane. Plane, as we could actually perceive this as like, it doesn't exist practically. It's a point in 1D, and it's actually also a line in 2D, if we perceive this. But we could also represent this as 3 points on the space defined actually in plane in the 2D space. And then the last time we saw that in order to compute this, it's very easy. So, but let us, instead of, like before we go into these things, just kind of like how we perceive a vector. So a vector could be perceived to have also dual representation. Any point in the 3D space is x and y and z. Could be, first of all, it is represent a vector, which is originated from the origin. This is one thing. So in similar, we have a dual representation. So it's the same thing. X, y, and z represent a point and represent a vector. And if we take all these vectors, which could be represented as like represent the entire space, because of all these are all the point in the space. But we know from algebra, very simple algebra, that any point x, let us call it y and z, could be represented as a combination, or what we call linear combination, of the vector, which will be x multiplied by, let us call it a, plus y multiplied by b, plus c multiplied by z. The requirement of a and b and c in order to form a base of the space to be independent, which is mean, if I'm talking about a vector like this, so all these points along this line, they are representing practically the same vector or the same ray. So if we're talking about this, will be, if this is the point will be a, b, and c, this vector, it's any k, a, b, and c will be along this vector. So if we're talking about, for example, the unit vector, which is all the points on the surface of a sphere, which is in this case will give a, will be the length of this vector will be 1, and all the points will be living on a surface of a 1-unit sphere, which is in this case from each vector will take 1 point, and this is will be able to represent it all the vector of the 3D space up to normalization. Any other like points will be represented as a vector of the unit vector multiplied by a scalar. Now, this is how we usually take the length of the vector, which is x square plus y square, and the second order root. And it's the same thing in the 3D space. And what we usually, this is what we call the normalization, dividing by this. And we add vectors, very simple. And dot product of two vectors, which is very simply, we can take it as u dot v, which is computed as x0 dot x1 plus y0 multiplied by 1 plus z0 multiplied by the z1. This is the vector, which is eventually will give us a scalar, which is often called scalar or dot product. And the value of this scalar, which is the same u dot v, actually there is no need for this because this is already a scalar. This will be the length of the vector u multiplied by the length of the vector u multiply the angle between the two vectors, which is usually if these are normalized vectors, people get the angle of just by the dot product. Okay. The cross product, which is we also explained in the last, if we have two vectors a and b, and we can do the cross product, which is give us a product or a new vector, which is perpendicular to the two vectors. And if we take a cross b, we will get ijk, and doing kind of computing this determinant, which is very simple. If the difference a cross b and b cross a is only difference in the direction of the normal. This is often things that if we confuse between doing A cross B or B cross A, will give us just change in the direction. And this is the simple like a formula to compute the cross product. Now, usually when we learn in high school about a line equation, we wrote it as y equal ax plus b, where a is the slope of the tangent and b is the intersection with the y-axis. Yes? We could also write as ax plus by plus c equals 0. So it's the same equation. It's the only thing that we normalize divided by the top equation by b, and then we will get the lower one. And the vector representation, which is often easy to use, which is instead of, if we have a point P0 and a direction vector, which will be V, then any line, any point along this line will be represented as P of t will equal P0 plus Vt. I think you all know this. If anyone just kind of having any question, just stop me. So I assume this is kind of, you have already seen this, but I'm kind of refreshing your mind about this. Was that clear? Okay. Now we also saw the representation of a plan. Pretty much the plan is very easy to represent as its normal, which determine exactly most of the property of the plane. So if we have plane, then we will easily kind of write the equation of a plane as x, y, z, the canonical terms, multiplied dot product with the normal, plus d, where d will determine the elevation of the plane. Now this could be written as xn, xxn, yyn, plus zzn, plus d. That's a... Now, one thing which we often do very quite useful is a point and line relation, point and plane relation, and then we have line to plane and plane to line, all these relations. So for example, it's very easy if we write an equation of a line y equal ax plus b, and then we could actually write the equation of a line, any point L on the line, any point x and y will be ax plus y plus c equals 0. Which is mean if I take point xi, yi and plug it in this equation, which is on the line, will give me 0. Any point above the line will give kind of a negative. Any point below the line will give us a positive sign. This is pretty much subdivide the space into 3 classes. One, points on the line, above the line, another, and below the line. The same thing with the plane. If we take point which is xi, yi, if we can write this as p of x, y, I, and zi, if we plug it in this equation, any point in the plane will give us 0, and any point above the plane will give us negative, and below the plane will give us a positive. So this is pretty much the same thing, but divide the entire 3D space into 3 classes. One which is points on the plane, one above it, and the other below it. Now, if we want to compute the intersection of 2 lines, that's very simple. We all learned this in high school. We just solve this like system of 2 equations, one representing the first line and the other one representing the second line. And then this solution will give us the value of x and 1. This will be the intersection point. If these point, the difference between point, like the 2 lines which are parallel, we know that this should be satisfied. This is 2 lines are like 2 points along the same lines. If they could be represented as what we have said is kind of independent, that they should be dependent, which is mean one of them could be represented as the other multiplied by a scalar factor. In a similar way, we actually think about the line and plane intersection, also when they are relation, when they are parallel, when they are above or below. The same thing with the plane and the plane. 2 lines, a line and the plane could actually intersect in a point or be parallel. The same thing with the plane and the plane could be parallel. And we can determine this either if the difference between parallel and completely kind of like inclusion, that one will be kind of like collide completely with the other based on if they have a common point or not. That's very simple mathematics, which is, I assume all of you know that. We usually refer to this as the Euclidean space or the Euclidean geometry. Now, it has a lot of very nice properties that we learned and we apply, and it works for almost all the things or the daily life around us. But it's not always a kind of convenient way to do kind of more like to other spaces. If we look at another, like I would say, domain, which is, we'll call it the projective geometry. And the projective geometry will look into the 2D space or 2D transformation. So what we mean by projective geometry, it's geometry that pretty much related to or developed, I would say, help us in order to kind of to understand the geometry of images. So one thing which is interesting is that we know that the line of the 2 rails are parallel. But are they parallel in this image? We know they are parallel, but if they continue these 2 lines, they intersect in one point. And this point depends where we take the photo of these rails. So if we take this one, the intersection will be somehow in the far horizon. But if we take image from the side, could be that way or could be that way, or depends where we take this. We often refer to this as the vanishing point. But what we are going to now to understand what this geometry is actually, what's the ingredient of this geometry and how it works and how it's going to help understanding this, the structure of these images. Now we'll return back to the very simple representation of a line. A line, we saw earlier that we could represent this as any line, which is L of xy, it's a function of xy, will give us ax plus by plus c equals 0, which is mean any point xy will be, if it satisfies this, it will be lying in this line L. Now, we could represent this, instead of all these equations, you could represent this as a vector, which is, in this case, we will be A, B, and C transpose. Transpose, which means even like a row vector or a column vector. Shows like this is mean a column vector. Now, this is what we call homogeneous coordinate. So what's the difference between homogeneous and non-homogeneous coordinate? We need to understand this because it's very simple, but it will help us kind of understand better the projective geometry. So if we have a point xy in the 2D space, this is an inhomogeneous point, which is mean we have one unique representation. But if we take this point and think about this as it's in the, like, elevate its dimension to be in the x, y, and w. I intentionally did not write z. That means it's somehow point in the 3D space. If any point will, if I take w to be any value, I practically take an intersection in the 3D space, creating a 2D. I take a plane, which is intersect the 3D to create a 2D space. That's very simple. And now, what I will require for W to have maybe specific value. If I take, for example, W to be 1, this is the normal homogeneous coordinate we use in all our geometric transformation, the Euclidean geometric transformation. Now, if we take now A, B, and C, this is what it will give us. It will give us very simple representation of this line, which is we say this point, which is in the 3D space, we could perceive it as in 3D space, it represents line in the 2D space. Now, one thing which is, if we take any value k and multiply the equation by k, we'll get the same equation here. We know from simple mathematics, if we divide, we'll get exactly the same line. So we could write this as taking the k inside, and what this is will lead that if we take A and B and C representing the line, it's will be equivalent k multiplied by scalar k. This is exactly any point along this vector, which is similar but not the same, which is any point along these vectors are somehow equivalent, or are equivalent in the projective geometry, or similar. Now this, the class of these points, which is what we call, if we take the normal 3D Euclidean space, take out the origin point, because it's not like a create, like we'll see why it's like we want to take it out. And this create what we call the projective space, or the projective 2D space. We shall refer to this as P2. So this is the projective 2D space. Now, if we think just to kind of to give you the motivation behind this, let us think about an image. Just go back to our world of images. And let us assume we have the image plane somewhere here, and this is the viewpoint. Now, if I take a vector, which is, let us assume this point is the origin. So if I take a point going through the center of this pixel, so if this is the pixel, which is the point, this is the viewpoint, which is I'm talking about. So this image came from this point in the world. Now, if we take this image, we don't know, one of the things which is this image could be of any point here. So this is exactly the kind of the motivation behind this representation, that it's a point in the image plane. In the image plane, it's a pixel, it's a point, it's an XY. It's a line which is started from the viewpoint. Let us call this is the origin. This is why we want to take it out of the space to get us all the lines. So it's this point and this line, they are equivalent in this sense. So because we don't know which point here is the image, or this pixel is the image of which of these points. The difference between this point and all these points, or is the same if we take this as x and y, and let us call this 1 just for simplicity. If this is distance, will be 1 of this image. Like all the points x, y, and 1 multiplied by then k multiplied x, y, and 1 will give us all the points in this. Now this is the motivation behind the projective geometry. Now, there is a nice things about the projective geometry, which is we say that if we have any point x, y, z, x, y in the 2D, will be represented with is like belong to a line ABC if and only if what we wrote in the previous line, ax plus by plus z equal 1. And in the same times, what we will get, this point on the line, and if we can write it like this, x, y, and 1, we added the 1, this is remind us by the homogeneous geometry we learned in like simple geometry, multiplied by the vector ABC, exactly will give us 0. So this is the requirement. What we realize there is here about the representation, if we take P transpose and multiply it by L, remember L represented as the ABC, which will be if point P on L, then P transpose L will give us 0, and L transpose P will give us 0. Yes? That's clear. And this is one of the things which is, it's very, now there is almost no distinction between a point and a line. And this is what we will see later about the duality. And now how we compute the intersection of two lines. If we have two lines, L and M, how we now compute the intersection of these 2 points? The intersection of these 2 lines. It will be a point in 2D. They must intersect in a point. always. Two lines always intersect in a point in the 2D. In the 2D space.
Lines
And if I have two lines, this is the 2D space. Any line in general 2D space. Like if I have 2D space, two lines, what I'm claiming that this is one line and this is the another. Yes? So they intersect in one point. If they are parallel, they will not intersect in a one point. Yes? This is when we learn in like we see that the two lines are independent and kind of like we were able to get like there is no solution for the equation if the two lines are parallel. There is either no solution, we will say, or there is infinite number of solutions. In projective geometry, two lines always intersect in a point. Always intersect in a point. And this is very simple. We take L, cross product M, and this will give us the point. Here is a very simple example. We have two lines. This is the first one, which will be phi. If I have this line, which is the L will be x minus 1 equals 0, and M will be y minus 1 equals 0. So these, if I look at these two lines, these are two lines. The first L will give x equal to 1, which will be this line. Yes, this is L. And the second one will give me y equal to 1, which will give me this line. Yes? So the intersection of these 2 points, if I can take the cross product of these I, j, k, take the two lines, L, what L will be? A, B, C, what L will be? 1, y 0, and minus 1. And the second one, M, what will be? 0, 1, minus 1. Yes? Cross product is actually pretty much computing the determinant of these matrix, which will give us I. This will give us, what will give us? This will give us 0, and this will give us minus 1, which is minus I, plus, this will give us minus. This is j multiplied by, I will write this. So j will be minus 1.
I think the previous one is 1.
Why 1? It's a, so that's 2. That's 2. Minus, it should be minus. And the last one will be k, will be 1, 1k. If I write it as a vector, this will be 1, minus 1, yes, and 1. Yes, this is minus multiplied by minus, which is mean this is the homogeneous. This will be x and y, which will give us this point. That's a simple case, and this is what we will get 1, 1, and 1. Now, if we take now a line that's connecting 2 points, if we have line connecting 2 points, it's very also the same thing. If I have 2 points P and Q, the line connecting or passing through this point is P cross product Q, which is again very simple. And now, if we write it as will be P, let us assume P is 0, 1, and the Q is 1, 0. The same thing we will give get this one. So what this is will give me these 2 points. Points will be 0, 1 will be this point, and 1, 0 will be this point, yes? Now, if I do the cross product of these, I will get the line, this line. Yes? Which is the what by cross product of these 2 points, I will get 1, 1 minus 1. And this is, I can write it as x plus y minus 1 equals 0, which is the equation of this line. That clear? Okay. So this is the part which is we are talking about the. Now, one thing which is what we will call what the ideal point, or the line at the infinity. So if we have, when we talked about like the intersection of 2 lines, we talk about the cross product of them. And when we learned in Euclidean geometry, we say if they are parallel, then they don't intersect. Here, if we have 2 parallel lines, what we will get, any 2 parallel lines, we can write them as A, B, C, and or A, B, any other C tag, or C prime. Now, what we will get, if we take these 2 lines and compute the cross product of them, we will get B minus A and 0. But in homogeneous coordinate, we don't have 0. All the idea we use, like when we think about this, the value there should not be 0. Now this, what we call, this is the point in the infinity, which is 2 lines which are parallel. Yes, they intersect, but they intersect in the infinity. We don't say they don't intersect, they intersect in the infinity. What's the nice things about this, that in the projection space, we don't need to take this as a special case, this infinity. The point is exactly perceived in any other point in the projection space. It doesn't need a special kind of handling. It should be computed like exactly as a normal point. Now, this is what we call the ideal point, or the point in the infinity. The line at the infinity is the opposite, which is we have 0, 0, which is, this is the line of the infinity. If we write it as kind of like, we'll take this, how this will look like, the line at infinity, we say ax plus by plus c equals 0. Now, if I take this as the line infinity, what I will get, 0 plus 0 plus 1, which is equal 0. This is, it doesn't exist only, and this is only correct in the infinity. So this is what we call the line at the infinity. So now, if I'm coming, like, this is why all the 3D space, the R3, the 3D space, if I take out from this the origin point 0, 0, 0, this is what will give me the projection 2D space. Is that clear? Okay. Now, one thing which is, when we talk about, when we learn in school, in high school, we say the point y equal ax plus b. We usually perceive this as this is a line, and this is the x and y coordinate system. And this is will give us, this is the line L. If we go to the another space and try to use different, this is, let us call, this is the a-axis and this is the b-axis. So any line L in this xy space, this is the x, y, and this is the a, b, will be mapped to a point. So the line in the XY space is mapped to a point in the AB space. So any point here representing a line here. Now, so what line represents here? This line, what's the equation of this line? Let us call it Q. In general, this will be exactly like which will be B. Let us call it alpha A plus beta. Yes? And it's just a naming convention. So instead of writing this is, we can write this as B equal X A plus B. Plus Y, which is mean a line here is represented as a point here. So this is what we call the dual space. So the space, the line here will be represented as a point here, and the line here will be represented as a point. This is what's nice about the duality theorem is any theorem which is applied to this one, there exists a dual theorem which is applied to this one. This is kind of an immediate case of the duality. Is that clear? Now let us go in the dual space. But before that, we know now, we learned on the what we have a point X in the projection plane. We have a line L, which is intersection of the 2 points, and we have the space, or like plane pi, which is the intersection of 3 points, or a line and a point. Now, if we take the duality, it's very easy to see the duality. If I have any point X and Y and W, this point pretty much is also could be perceived as a line, A, B, and C. There is no difference between them. A line and a point is exactly when we saw in the vector space, a vector and a point are the same thing. There is no difference between a point and a vector. So here is the line, this duality that means a line is and the point are the same. Exactly as a vector and a point are the same in the normal Euclidean space. Now, if we take from the duality, if we take point which is X on the line L, which is mean X transpose L equals 0, is exactly the same. We can write it as L transpose X equal to 0, because we could perceive this as X as the line and L as the point, which is exactly the same. This is we normally we already perceive that a point and the vector in the Euclidean and real space are the same. It's in the projection space, like the projective space, projective space the same. A line and a point is also the same representation, because we will have two lines intersect in the point X, point which is common to two lines, the intersection of two lines computed as L cross M. And the same thing, 2 points, which is create, or like the equation of the line that pass through 2 points, P and Q, computed as P cross Q. So if we take now the parallelism between L and M and X here could be as P and Q and L. They are the same. Here we take two lines, which is the point they intersect, and here we have 2 points and the line which is passed through. that clear? Any question? So this is simple. Now, one thing which is, before we going into conics and what conics mean, if let us assume I have a circle, this one, and if I'm going to take a camera and take a photo of this circle, what the possibilities or what the images of this circle could be? What?
Oval shaped.
Could be, the simple things would be kind of like an ellipse. If I take a photo from here or anything, not completely perpendicular to the plane of this, I'll get, like, if it's perpendicular, the camera is completely perpendicular, I get exactly the same, like, circle. If I'm taking from like tilted angle, I will get an ellipse. And then what others I can get? Line. Okay. I can get a line, exactly. A point, how I could get a point?
Far away.
Infinitely far away. Okay. This is because we are looking at the discrete domain, we can get a point, but it's kind of like a since we are talking about like a continuous, you will not get a point. Now let us take about something which is unique. Let us think about the viewpoint and connect the viewpoint we have, the viewpoint, with lines on the boundary of the circle. So what we will get? So what we will get actually a cone, which is from if I take the viewpoint and connect it with the lines on every point on the circle, I'll get a cone. Now, any image which I will take will be intersection of a cone. So this is practically what I will get. Now, is that clear? So if my viewpoint here will be connecting to every point on the boundary of the circle, I'll get a cone. Now, every image I will take based on the position of my camera, it will be, of this circle, will be an intersection of a cone. Now, the simple one will be an ellipse. But conics, like, was studied intensively almost from the 10th century, even before. And people think what really the form which we will get. So we can get a circle by intersection of cone. We can get an ellipse by, if we have an intersection of a cone, which is the cutting plane is not really kind of in an angle, but if it's too much, like the angle is too big, what we will get parabola. And if it's at the two sides, the cone and the continuous, we get a parabola. This is usually, we refer to this as the conic intersection. We have sphere, we have ellipse, we have parabola, and we have hyperbola. Is that clear? Okay, now all the conics, the nice thing about these conics could be represented as a quadratic equation, which is mean we could represent it as ax squared plus bxy plus cy squared plus dx plus ey plus f. So if we take, for example, how lines, like it's this equation, represent a circle, how it will be ax squared plus y. Any circle will be by squared equal r squared, which is in this case will get, will be call it different things. Alpha. In this case, what we will be? Alpha will be A will be alpha. B, what will be what the value of B will be 0. C will be 1, or beta in this case, sorry. D will be 0. E will be 0. And F will be minus r squared. Yes? So I can represent this as a vector, which is in this case alpha 0, beta 0, 0, minus r squared. This will give me a circle. So I write this as a vector of how many dimensions? 5 dimensions. So the same thing I can write an ellipse, which is what I will get from this circle, like from this quadratic equation. Now, I can write any of these conics, like I can represent any of these conics using this equation, which is now any point in this could be also represented as this matrix representation, which is X transpose C and X, where C will give us represented as this equation, where these are the A, B, C, D, and F. We can write this as a matrix representation. As we see here, we have 5 degrees of freedom. Why we have 5 degrees of freedom? Because we have, how many variables here we have? 6. So why it's 5 degrees of freedom?
So the 6 values of the value of the equation.
The 6?
The positive is basically the value of the equation.
Yeah, we can divide it by f, it will be 1, and we'll give the same thing, just different names. So this is, yes, because we have only, like, one will be dependent and the others will be free. And here we have, what?
What if f is 0?
This is something, we assume here f is not 0. Now this is, if we divide it by f is 0, we can choose another one and divide by it. It's the same. So whatever you take one which is not 0 and divide by it, you will get 5 degrees of freedom. Now, if you realize this matrix is not a general matrix, it's symmetric. This is the axis of symmetry, and it's symmetric. It's pretty much what it represents, since we always can divide and give 1 here. What it's a ratio representation. And this is exactly what it's a ratio between these variables. It's a ratio between these variables. Like if we think about the axis of these shapes, like the ratio, which will be, for example, the circle will be the ratio between the two diameters will be 1. The ellipse will be different. The same thing with parabola, hyperparabola. Now, a point x, I, y, I will be in a conic if it's satisfied this equation, axi squared plus xiyi cyi squared plus dxi, and this is plus f will give us 0. That's clear. Now, and we can write this as a vector representation, and this will give us 0. Now, how many points I need to define a conic? If it's a circle, how many points I need to define a conic? Circle, Why? If I have 2 points, I could draw this circle. Sorry, I'm not good at drawing. I could draw this circle. I could draw infinite number of circles. So 2 points is not enough to draw a circle. 3 definitely is enough. Now, but the circle is the most restricted representation of a conic. Because we had alpha, beta, and r. So how many points I need to represent an ellipse? 4 points. 4 points is enough to represent a circle? Yes. Now, how many points I need to represent a parabola? No. 3 points. Let us look at the equation of the parabola. Ax squared plus bx plus c equals 0. So 3 points will be enough. Now the general conic, we need, if we are going to solve this equation, like these variables, how many variables we have? Because this vector determine the conic. So in order to be able to solve this, how many equation I need? What's the dimension of this matrix should be? Or the rank of this matrix. I have 5 variables. How many equation I'll be able to solve them? 5. So we need 5 points to kind of determine a conic. Every 5 points determine uniquely a conic.
5 points
in the
R6.
No, 5 points in the 2D, not like 5. Every points will give us x exactly like we have there. X0 squared plus x0 y0 plus.
Yeah, I mean like 5 points inside a space of 6 dimensions.
The conic is a space of like 6 dimensions. So this is, we can perceive that the conic space is 6 dimensions, and any like 5 intersections will give us will determine which conic, the point which is we are talking about or we are considering. Is that clear? Now, how we know what's the important thing about is how we determine the tangent of a conic. So if we have a tangent T and the conic C, so the tangent at point X, the tangent of conic C at point X is T. How we compute T? What?
Divide through the pi. General equation, divide through the pi.
Yeah, we could compute the derivative of the conic, and then assign the point in the derivative of the conic. This is one valid option. The other is practically take the matrix representation of a conic and multiply it by x. So recall that C is a matrix 3 by 3, and x, the point, will be, in this case, will be x, like, because it will be x, y, and 1. And we multiply the matrix by this, and will give us the tangent. This will give us the tangent at point x, the tangent of conic C at point x. And notice that we don't need to worry if this is a circle, ellipse, parabola, or hyperbola. Any conic will be able to do this. For any conic, without really kind of taking into account what kind of conic is this. Now, if we take the line L, is a tangent of a conic. So now we have a point, we compute the tangent that pass at this specific point. Now if we have any line, and we have a conic, when we say that this line is a tangent to a conic, or a tangent to this specific conic, if we take C star, and I will determine what C star, which is after I multiplied by L and L transpose, if this gives me 0, this means this line is a tangent to this conic. This line is a tangent to this conic. Now, what we call by C star is pretty much the inverse matrix. But the requirement is that the inverse matrix to be of the same rank as the matrix itself. That means during the transpose we don't lose dimension. Is that clear? Because in the transpose, if the matrix is not of a full rank and we inverse this matrix, what we will get less dimension, like smaller rank. Now what we require here that the transpose, like the matrix C star, is will be valid for a matrix which is of full rank, which is the inverse of matrix, but we demand that this matrix be of a full rank. So if we take the same thing with the duality, so if we have, this is a conic, the set of lines, the set of tangent, infinite number of tangent of this conic, practically this is the dual representation of this conic. So this will be the conic tangents, which is the same as the conic, because a line and a point are the same. Recall that we say a point X which is satisfies or in the conic will give us this value, but it's Cx also gives us the tangent of the conic at point X. Is that clear? So here what we have the conic and the tangent representation of the conic. Is that clear? That's pretty much the duality of this. Now this is what we mentioned, that the requirement of the rank, which is a full rank, which is what we call degenerate conic. The degenerate conic, which is when we have the rank of the matrix C is not as the rank of its inverse. So which is mean if we take C star and kind of like making inverse again, we will not get C. And this is why it's not in a full rank, and this we will call this degenerate conic. Degenerate conic could be a line, but it will not be represented by a conic. Clear? Now we will go to projective transformation. Projection transformation, which is a mapping from a point in the P2 to another point in a P2. This mapping is a projective if and only if it's a preserve linearity. What does it mean it preserve linearity? That means it's a preserve linearity that if I have 3 points in a line and H will be my light transformation, H is projective transformation or projectivity, we call it, on F and only F, they applying to P and Q and R. The HP, HQ, and HR will be along the same line.
The same line?
Yes. Line. So because line will be mapped to another line, but not necessarily the same line. So what we will get, I will get again. Projectivity is a projective transformation, which maps a point to a a point in the P space or P2 space, it's called projectivity. Not any transformation in the P2 space is called projectivity. Projectivity is a kind of transformation that every 3 points, which are on the line, applying the transformation H to these 3 points will create a new 3 points along a line, which belong to the same line. This is why we call projectivity mapping is preserve linearity. To preserve. Lines will be mapped to lines, not to something else. This is one thing about this, which is also often projectivity called collinearation. That means it's preserve the linearity of the points. Or often it's called homography. This is what in image processing or depth images we often call the homography. So we need the homography of an image, which is mean the transformation in the projectivity or the projective transformation. And now, how we determine that a projective, like a projectivity or any mapping, I earlier said not every mapping in the projective space is a projectivity. So projectivity is a transformation, which is one thing which is we say it should preserve linearity. And there is a very simple theorem. If we can represent this mapping H as a 3 by 3 matrix H, then it's a projectivity. Which is mean if and only if there exists a non-singular matrix, non-singular, which is mean its inverse exists and its full rank. This is what non-singular. And this is 3 by 3 matrix H, such that the mapping H of X would be exactly like X multiplied by this transformation. Which is what we said, that it has to be linear transformation represented as a 3 by 3 non-singular matrix. It's very easy to check that it's non-singular matrix. How we can check that it's non-singular matrix? We can check through determinant, or we can actually diagonalize it, and we will get, or try to compute the inverse, and you will get a different rank. Okay, and so this should be true for any point in the P2 space. And this is, if we can write this, is if we have a point this is the projectivity X will give us a point H tag. Now, what's the degree of freedom of H? If it's 3 by 3, how many terms in the matrix H? How many terms in the matrix H? 9. One of them we can divide it by its value, we'll get 1. And how many degrees of freedom remains? 8. So this is 8 degrees of freedom in order to determine homography. This is what we will often need in order to rectify an image. This is the very kind of like basic transformation we would like to apply in order to what we call calibrate a camera or rectify an image. So I'll stop here, and I will continue next week. So I will start next week from the projective transformation. Okay? So we'll see you next week. Sometimes I think a week before Christmas or a week after Christmas, I think we will not have a lecture. If you have a kind of a limitation that at some point you don't think that this week is maybe very few people will be able to attend, we can like cancel the lecture. We are not really running in kind of like a really course with it's pretty much a reading group. The idea that I'll go over kind of like a preliminary material in order for us to understand what really projective, and then we will kind of like run as a seminar. So we'll be reading a paper and discussing like these kind of related to this kind of depth images and reconstruction and the multi-view geometry. But I'm trying to create kind of the basic knowledge in the beginning that we can always engage kind of in this discussion. Okay, so we don't, if you think, just tell me which kind of Friday you don't like. It's maybe not recommended to have a lecture. We will postpone it because the idea we hopefully will try to run it till next September. Maybe not continuously, maybe if there is a week here and there, we will be able to cancel, not a problem. Okay? Okay, so have a nice weekend and see you next week.